probably not finish it today. So we're at page 11. Are there any questions before I continue? All right, so where did we leave off? We had defined the Rademacher complexity of a class of functions, which was this expected value. There's two sources of randomness, the NIID data points and these new Rademacher random variables, which are basically coin flips, plus or minus 1. So this attaches a real number to the class of functions. Now, a piece of notation we want to keep in mind is if I take this class of functions and I write this down, where these are just fixed points, not random points, then that refers to the set of all vectors we get by evaluating the function at those endpoints and letting f vary over the class. Yes? Update on the waitlist situation. I'm going to wait and see what it looks like today. It seemed to get a bit better last day, and if everybody fits in today, I think I'll just tell them to clear the waiting list. I'm pretty optimistic, though, about the waiting list. Okay. Probably what I'll do, though, is you can't get in the waiting list unless you get the class on time. That'll be the defining rule. There's another fact we're going to use, which we proved in 705, and I want to remind you of it. If you've forgotten this point, it's proved in these notes too later on in the notes. I'll tell you the correct lemma in a minute when I find it. I think it's theorem 31 later on in the notes. We did it in 705, but here it is. Suppose the moment generating function of xi satisfies this exponential inequality. What did we call that? Sub-Gaussian random variable. And an example of things that are sub-Gaussian, well, Gaussian, but also what? Things that are bounded, right? Automatically satisfy that. And one of the things we proved about that was that the expected value of the maximum of a bunch of random variables is less than or equal to that sigma times the square root of 2 times the log of the number of variables. The max increases with the logarithm if it's sub-Gaussian, which includes bounded random variables. So we're going to use that fact now to try to put a bound on this Rademacher complexity. And so this proof is very simple, but it's very fundamental in the sense that it uses the basic ideas underlying all of this stuff. And so here it is. Here's our bound on the Rademacher complexity. I'm going to go right from here to here. It's this expected value, and the key here is that there's two sources of randomness, right? The z's and the sigmas. So what we're going to do is first condition on the z's. So I'm going to look at the expected value of the soup of this thing, of that quantity. But now I'm going to condition on z1 to zn, and then take a second expected value. That's the rule of the iterated expected value. The point is that when the z's are fixed, these are just numbers. Okay? And remember, I should have said, we're in the realm, let me remind you that we're dealing with binary functions right now. So these are just ones or zeros. These are plus or minus ones. But now these are just numbers because we're conditioning on them. And so this is just an average over the sigmas. So when I look at this expected value, the conditional expected value, taking the soup over f, what am I doing? I'm just taking the soup of f of z1, f of z2, f of z3. That's precisely this thing. It's precisely the maximum over all vectors. Okay, so I could, in fact, I even rewrote this in the notes as the expected value of the maximum of, I called this whole thing S of v. All possible vectors, you let v vary over all possible vectors. Because remember, we're conditioning on the z's. They're fixed. So when I feed these in here, we're just looking at a vector like this, and we're taking all possible such vectors. And we're taking the expected value of that maximum. And these random variables are just now the sigma I times one of these things, which is just a number. Okay? And actually, I should say that think of it as 1 over n times that. So we are precisely in this situation, that the random variables are the sigmas. In fact, the random variables are really, think about it as sigma vi, where vi, I mean f of zi. This is in between minus 1 over n and 1 over n.
You divided the vi by n. What's the definition of vi?
Oops, yeah. Thank you. Yeah. So it's easy to check that this condition is satisfied with sigma squared being like 1 over n. So despite the fact before we were taking a soup over an infinite class, but once I fix the z's, f of z1, f of z2, this only takes finitely many values, at most 2 to the n. And so I can apply this thing. It's the expected value of a maximum. So the inside of this expected value just becomes precisely this quantity, which is 2 times the log of so I'll write it like this: the number of possible projections, and the n is coming from the 1 over n in front. So clear what I'm doing? The only thing random is the sigmas. I apply the fact that now we're taking a maximum once we condition over a finite class of vectors. We're no longer dealing with functions.
There is a sum. How do you go past that?
What sum?
The sum of the I index I.
Oh, yes. But the sum, there is a sum there. The random variable, so if you look at what I've left out some of the I haven't written everything down that's in the notes. So this thing I called guess includes the sum.
Can we bound the sum as n?
We don't want to bound it by n because that would increase too quickly.
But you thought the bound is the each term, the sigma I, vi is bounded. But you do not say that the sum of the sigma I with vi is bounded.
That's true, but if you look at the, I think I left a step out here. The expected value, what did I do with the sum? I've bounded it. We're taking the maximum over all f's of this sum.
That sum could be n, right?
That sum could be n. No, it can't.
No, but the maximum you take is not the I.
I agree. The maximum is not over the I. I've definitely left out a step to deal with the sum. You're right. S of the I, S of the I, expected value of that, expected value of that. I'm taking the maximum over all vectors. Okay, there is one step missing. I'll fill that in. I'm forgetting it right now. You're right. There's a step missing in here. The result's correct. I'm positive of that. But I certainly don't want to do the max, put the n in because that would make this too big. I think.
I mean, the sum is maximum n, then we take the average, so the maximum is 1. The average maximum is 1. Right.
The average maximum is 1.
All the sigma i's become 1, and all the fz's are also 1. So that adds to 1.
No, we need to use the sub-Gaussian property for this one.
Sigma is, if you say that sigma is 1 over n, then there will be a squared in the square root. But since
Yeah.
there is n, I think the bound may be something behave like 1 over root n. The sigma.
Yeah, I think it does, right. So I think what's going on, again, is I left out a step, which is maybe it's just I think what you're saying is the expected value of the sum is less than the sum of the expected values. That adds an n, but then the sub-Gaussianity has a 1 over n, which brings in a 1 over n squared. And so we end up with a 1 over root n. So I've probably just confused you. I'll send out page with the extra steps in it. There's definitely a step missing. Yeah, good catch. I think I just shortened that too much. But the result, though, is correct. And let me just say what we're using, though, is the key fact here is that we're starting with an infinite class of functions. How are you going to bound that? But once we condition on z, this can only take finitely many values. And then we use the sub-Gaussianity to bound the expected value of the maximum. And again, there's another step bringing it inside the sum that we'll fix later. However, there's another step here, which is, what is the largest number? How many possible things are in this set? By this I mean the set of all possible projections. That was the definition of the shattering number, right? The shattering number is the maximum that could be. Okay, so, and this is but the outer expectation doesn't even matter anymore because this is a constant. It's funny that I've probably used these same notes for 3 years in a row. No one ever caught that mistake before, including me. All right, so where were we? This is 2 log times the shattering number. So modulo that one step will fill in. The thing here is we can bound and this is for binary functions, remember. The Rademacher complexity can be bounded by 2 times the log of the shattering number over root n. That's why we're interested in the shattering numbers, because that's often something we can compute, as you know, for different classes of functions. In fact, let's think this through a little bit further. Remember that if the VC dimension was finite, there was some sort of bound on the shattering number. Suppose the VC dimension is some finite number d. Remember I'll remind you of this since, again, I know it's been a long time since we looked at this, and I'm sure it's in here. Again, yes, Sawyer's lemma says that for large n, this is less than, whenever the VC dimension was finite, this was one of the critical facts, remember, that when n is large enough, bigger than the VC dimension, the shattering number can only grow, basically the key thing here is n to the d, right? Think of this as, for the most part, like n to the d. It grows polynomially in n instead of like 2 to the n. And if you use that fact here, think of this as, again, as like n to the d. What is that saying? That's like 2d log n over n. This is what makes VC dimension useful, is the Rademacher complexity is somehow the more fundamental quantity, but if you have finite VC dimension, we can bound it above, at least it might be loose, but we can bound it above by something involving the VC dimension. So you don't actually need to compute the Rademacher complexity. This bound actually is not as tight as it can be. There are much longer proofs that get rid of the log n. The log n is actually not necessary, but the proof's much longer. But the more important thing is, how does the dimension enter into it? Well, it's d over n.
Is there a generalization over the f? Right now it's binary functions.
Yeah, there are generalizations for different f's. Right now it's binary functions. We need that because that's the only way we've defined VC dimension. Yeah. I think we'll see if we have other bounds. I think that might be the only upper bound I included in the Rademacher complexity. But there's other measures of complexity besides Rademacher complexity that we're going to use anyway when the VC dimension is infinite, for example. Okay, so I'm sorry about that one error there, but other than that, I hope I didn't confuse you too much, that there's this very simple relationship between Rademacher complexity being less than something involving shattering number or VC dimension. We did shattering numbers in VC dimension in first term. I reminded you about it last week. In case you forgot, it's on page 12. I've reminded you of the VC dimension and the Sawyer's lemma, which is this fact. Okay, so if you've forgotten that, you should review that. I also put a little reminder for you on top of page 13 of some of the common classes of sets. Remember, a class of set and a binary function are the same thing. You can think of the indicator function for a set is a binary function. And I just reminded you of what some of the VC dimensions are. And you can look up a lot of other ones. People have worked out the VC dimension for many, many different sets. I also included the tighter bound, theorem 19, and a reference to a proof if you want to see the longer proof. That gets rid of the log n. It's not, to me, the log n is not a big deal, but. All right, so that was Rademacher complexity. We're going to use that in several places. But for now, we're going to put that aside. I want to talk about today one of the big theorems that gets used a lot, for example, in classification, which is this famous theorem, the Vapnik-Chervonenkis theorem, which you can think of as simply the extension of Hoeffding's inequality to deal with classes of functions or classes of sets or sets of classifiers is where it gets used the most. So this is page 14. So we're going to let f be a set of binary functions. Again, think of them as classifiers if you like. And we did this theorem in 705, but now we're going to prove it because the proof has 2 or 3 tricks in it that get used quite a bit. So the theorem says this: for t large enough, we have that. Let me put it down and then remind you of some notation. In fact, I think I skipped this notation last class, so I'm going to tell you what it is in a minute. Let me just write down the theorem. All I mean here, Pn of f is just the sample average. That's just short for this. And P of f is just the actual this is the true mean and the sample mean. So this is just saying that the maximum deviation between the observed mean and the true mean, the probability that's bigger than t, is at most, this looks like basically like Hoeffding's here, and then the shattering number. Okay? So again, the really important thing here is that for some classes of functions or classes of sets, like finite VC dimension, this is like going to grow like a polynomial in n, but this is decreasing exponentially in n. That's what makes it all work. So let's prove this. This is the key proof. If you've never seen it before, it's a really beautiful, simple proof. And it uses the same basic reasoning we just used a minute ago, which is that really, although it's an infinite class of functions, when we look at an infinite class of functions, binary functions, over finite number of data points, it's really like a vector, and it can only take on a finite number of values given by the shattering number. But the first step is a very clever trick, which is called symmetrization, which gets used a lot in this area. There's a branch of statistics called empirical process, or probability theory called empirical process theory. It uses this symmetrization trick a lot. So this is something which gets used all the time. And the idea is this, is remember we have our data, z1 to zn. The following very cool trick is you create what's called a ghost sample. So this is not a sample you actually see. That's why it's a ghost sample. But it's just something used in the proof. You imagine a second sample drawn completely independently from the same distribution. So z1 prime to zn, make sure I used prime. I think I used prime, yeah. Also drawn from P. It's only going to be something used in the proof. Okay? And let me give you the idea, first of all, what the symmetrization is. Then we'll state the theorem, and we probably have time to even do the proof. So it's the following idea. Let's just look at, suppose I was comparing a sample average to its mean. And suppose I wanted to prove something about that. And if this was based on an average of n data points, this can only take really finite many values. Say if they were binary random variables, but this can take on infinitely many values. But you might get an intuition that comparing how likely is this to be big should somehow be related to the following question. Instead of comparing x bar to the mean, what if I just got two people in the room and gave them two samples and each person computed x bar? And consider instead this difference. The difference between two means from two different samples. And intuitively, since they both have mean mu, saying that the probability that this is big is unlikely should somehow be related to saying the probability that this is big is unlikely. You know, if x bar can't be very far from the mu, then if you and I each get x bar, we can't be very far from each other either. That's the intuition. And we'll make it precise in a second. But the nice thing about this is if these are averages of binary random variables, then again, this is now a finite thing. This can only take finitely many values, whereas before it could take infinitely many values. So let's state it more precisely. This is lemma 22 at the bottom. And it's a key trick in this. And so what we're doing is, this is what we're interested in. This is what the theorem is about, is this quantity. But again, P of f, that's the mean of this function f. As f varies over this infinite class of functions, this can take many, many different values, infinitely many values. That's a difficult thing to deal with. So the symmetrization lemma says if we introduce this ghost sample, then this is less than 2 times the probability of the sup over f and the prime just means, this is the average over the original sample, this is the average over the ghost sample. And we're going to compare that average. So that's just, this is this average minus this average is bigger than t over 2. This is what we want to show. This is the symmetrization lemma, it's called. It removes the P of f, this unknown mean. Instead, we're comparing two samples, the original sample and the ghost sample. There's a little bit of a loss of constants, right? This becomes 2, and this gets changed from 2t to t over 2. OK? So let's prove this. We'll just go here. So let's look at this quantity that we're bounding. That's this thing. Let's pick a function in the class. Let's call it, I think I called it fn. Yeah, fn, which actually maximizes this thing. And if there isn't a maximizer, you can choose one that's arbitrarily close for any epsilon greater than 0. We'll just, for simplicity, assume that it's actually achieved at some fn. That's fine. So there's some function in the class which maximizes this over f. That's what we're interested in, right? The probability of the sup. Well, we have to be careful because that function is data dependent. The function that maximizes this quantity will depend on the z's. So we have to be careful that this is not a fixed function. This is a function which depends on the t's. OK, so the first thing to check is from the triangle inequality, the following implication. If Pn minus P, the difference of the expectation and the integral, is bigger than T, and if P and the ghost sample are small, then, so I'm saying if this is far away, but this one's close, then clearly these two things must be far away from each other. That implies that's just the triangle inequality. Let me just draw a picture of it, though. Is that if this is Pn of f, and I'm telling you that the ghost average is close to that, so let's say it's here. But the original sample is far from this. Wait, this one's supposed to be the ghost. If this is close and this is far, then these can't be too close together, right? That's just the triangle inequality. I wrote it out for you right there. That displayed line is just the triangle inequality. But I hope the picture just makes it clear. I'm not saying anything complicated. If this is close and this one's far, then these two can't be too close together. That's where the T over 2 comes from. All right. So this and this implies this. So therefore, the indicator function for this is bigger than or equal to the indicator function for that. I'm just repeating the same thing now. I'm just going to write down the indicator function for this being true. So this is, what do we have? That the indicator function for Pn minus P, that's that thing, of Fn, bigger than T, and, I'm putting the and in, P minus Pn prime Fn implies that's bigger than, I'm just rewriting that statement in terms of indicator functions, okay? All right. Now the key is we're going to just take the expected value, but remember there's two sources of randomness here. There's z1 to zn and there's z1 prime to zn prime. So first I'm going to take the expected value only over the ghost sample. These are all independent. So I'm going to take the expected value over the ghost sample, and these are independent. This is based on the ghost sample, and this is based on this. So, and of course, when I take the expected value over the ghost sample, this is just a constant. We're keeping z1 to zn. We haven't done anything to those yet. So I get the indicator function of Pn minus P Fn bigger than T times the probability, and I hope this is clear, but I just mean here probably only treating these ghost samples random. Minus Pn. This is getting a little bit laborious, but bear with me. And that's also just over the ghost sample. Make sure that agrees with the notes. Yeah. However, I want to argue that I think I lost a 2. Yeah, t over 2, right? The claim, I now claim this is bigger than or equal to a half. So I can just sneak a half in there. Why is that true? That's just Chebyshev's inequality. Let's just verify that. The probability that this quantity, this whole quantity, what have we got here? It's a bit of a mess, but the main thing is what's random in here. This is random, but it depends on the original data. We're only talking about the randomness over the ghost sample. The only thing that's happening here is this is just an average over the ghost sample. And so this is just like x bar minus mu, in other words. So I can take this. This is less than or equal to by Chebyshev's inequality, or just, yeah, Chebyshev's inequality, or Markov's inequality, if you square it, is t squared over 4. So that becomes 4 over t squared times the variance of that quantity. The variance, remember, everything here, I'm going to keep putting primes to remind you. These are all, we're only dealing with binary functions. This is between 0 and 1. The maximum variance anything can have, any random variable can have, is a quarter if you're talking about binary random variables. So this is less than or equal to a quarter times this. So this is 1 over, oh, I forgot the n. There's n things here. This is less than or equal to n t squared. And one thing I should have mentioned at the beginning is we're only doing this for t large enough. I took t to be bigger than 2 over root n, which will certainly be true for any fixed t as n gets bigger, which makes this less than or equal to a half. So the probability that this is bigger than this is less than a half. Therefore, the probability that this is less than this is bigger than or equal to a half. I just computed the opposite event of this. So this is less than half. This one's bigger than a half. So we're almost done. Okay, because now I have that the indicator function times a half is less than this. I can bring the half over here and make that a 2. That's where the 2 comes from. Okay, so what I've got now is that, let's see, I'll just keep going here. The indicator function so I have this term, the indicator function, times Pn minus P Fn being bigger than t is less than or equal to, and I'm taking again this 1/2 and bringing it up here, which makes it 2 times the probability that it's less than t over 2. We're almost done. Okay, so we get the indicator function of this. It's less than or equal to 2. Now I'm going to write out what this is on the inside. Because remember, we chose Fn was a particular choice of this. So this is less than or equal to the sup over F. Pn prime minus Pn. And that's it now, because now, don't forget, the original data are still random, z1 to zn. If I take the expected value over z1 to zn now, I get the probability of this. But remember what fn was. It was chosen to be the soup, right? So this is just the probability of the soup is less than or equal to. When I take the expected value over that, I get rid of the I'm taking the expected value now over, actually, I'm taking the expected value over z1 to zn. And so this, and by the way, don't forget, this has the same distribution. z1 to zn prime have the same distribution of z1 to zn. And so that's the same as the probability of the soup over f I think I got everything there. Okay? So if it got confusing, just think about doing this with x bar 1 and x bar 2, where it's a little bit simpler and you'll get, it's basically the same thing. The only trick is it was convenient to pick the f, instead of keeping to write that soup, we find the fn at which this is occurring and stick that into the proof.
Can we ensure that this fn exists in our function?
No. So what if it didn't exist? You'd have to repeat the whole proof and say, for any epsilon greater than 0, find an fn that gets within epsilon, and you'd have to do the whole proof for that, and then conclude that you'll be an extra epsilon, and then say, since it holds for every epsilon greater than 0, you would be able to get the result. So it's just a bit messier.
How do we know it's the same fn for both?
It isn't. It doesn't have to be. We just, because that's why we computed, we've throughout the entire proof, we keep the outer sample, the z1 is fixed, and so that's just some function fn. You want to know, and this was computed at a particular fn that's still less than or equal to the soup over all f. It's only in the last step that I substituted back in the definition. It's a very, very clever trick that now I've reduced it to 2 sample averages that I have to bound. Okay, so this idea of introducing this ghost sample is something that comes up in a lot of different places. There's a bit of manipulation, but we never used anything more than iterated conditional expectation, Chebyshev's inequality, and the triangle inequality. And now let's prove the VC theorem, because with the symmetrization, I've now reduced it to, let's just now bound this quantity. That's what we have to bound.
Sorry, where do we use the ghost sample distributed the same way as the rechain? Couldn't we just take like any?
There's places in here, no, where I assumed that, if you look carefully, you'll see that we're using this fact. The expected value of this quantity is PF, but that's also true if I put the ghost sample in. And somewhere in here, I'm forgetting where I used that fact. So it has to be drawn from the same distribution. Otherwise, I would have been subtracting off, probably when I did Chebyshev, I wouldn't have been subtracting off the mean otherwise.
That's probability solved for both samples, right?
That's right.
Where do we use this for? But you could have used Chebyshev for another.
No, but it wasn't centered around that. Let's see, where did we do that? I've lost it, but I think I erased it. But go through the steps, and you'll see if you don't have this for both for the true sample and the ghost sample, the proof won't work, actually. Yeah. I mean, it would be kind of miraculous if you could throw in any distribution there. It has to be the same distribution. Not only that, but for other things, we're going to see that if it's not a ghost sample, later on we'll see that for other proofs, we're going to use the fact that the distribution of Zi and Zi prime, you can switch that. It has the same distribution. They're equal in distribution. That's something we'll use a bit later on in some of the proofs too. So that the idea that the ghost sample comes from the same distribution is important. So let's prove the VC theorem. So I'm just going to bound this guy. And again, we're going to project the sample. So now let's call V the set of vectors I get. But we're going to use the original sample, and we're going to introduce a ghost sample. OK, so we're going to have, which way did I write it here? Yeah, Z1 prime, Zn prime, Z1, Zn. So we're implicitly introducing now projection onto 2n random variables instead of n. That's why in the VC theorem you see a 2n in the right-hand side of the theorem. It's because of this introduction of the ghost sample. And so when we take an f and we evaluate it at the true sample and the ghost sample, we're getting a vector of length 2n. And the set of all such vectors I'm calling V. And in particular, anytime we have a quantity like this, say I take the ghost average minus the true average, that's the kind of thing we have here, we can think of that now as, what is that? That's really just a sum of, let's call them Vi prime minus sum of Vi's. Make sure I did the same. But you can really think of it as one big long vector where you're summing up the first n minus I equals to n plus 1 up to n. Right? So in other words, these averages just involve averages of things in this set of vectors. And we're going to use the same trick we did before now, that the probability that the sup over f and f of this thing can only take finitely many values. That's the sup over this class is really equal to the max over this set, the maximum over all vectors of that form of, let's write it this way, Pn prime V minus Pn V. Right? These are just thinking of these as averaging these vectors now. There's no more true mean. There's just the function values. And the probability of a max is less than or equal to the sum of that. We're doing the union bound. And that's it. This, what have I got? The sum of these things, how many things are in here? That's the shattering number. There's at most that many. And this probability is bound by Hoeffding's inequality. That's the Hoeffding. The only thing is there's a t over 2 instead of a t. So that's why we get e to the minus t squared over 8.
But the bound of the variable is minus 2 to 2.
Sorry?
The bound of this value, the p and pi.
Right. Are you talking about the 2 out front?
No.
No?
It's bounded in minus 2 to 2.
Right. So that's all been put into this. If you put it in, I think you get e to the minus n t squared over 8. I'm pretty sure that's right, except that I lost a 2 probably, yeah. There's probably, yeah, there's a 2. Yeah, you have to do Hoeffding's inequality, taking into account, you're right, the range of the variables and the fact that it's a t over 2. I believe I got a t squared over 8 there. You get something else? All right, well, maybe it's t squared over 8 or t squared over 16. I think it's t squared over 8. I think, but I make arithmetic mistakes, so it's possible. It's t squared over 4, t squared over 16. I'm pretty sure 8, I checked it, but you can check that yourself. Yes, so then I lost, what I didn't keep track of was that the original thing we want is 2 times this probability. So what I really wanted to bound was 2 times this, which makes this a 4. And that's it. That's the proof of the famous VC theorem. Okay, there's 2 big tricks there, which is introducing this ghost sample or the symmetrization reduces something infinite to a finite, a combinatorial thing. And then, using the fact that once it's finite, you just take the union bound and apply Hoeffding's inequality. The real intuition here is that even though you're dealing with an infinite class, when you apply it to a finite set of data values, it can only take a finite set of numbers. And if that finite set is not too large, then this probability won't grow too fast. At least assuming this is something that's not growing fast, right? There are cases, remember, where this could be infinite, where this could keep growing with n. But this is useful in the cases when this doesn't keep growing. And in particular, with finite VC dimension, this is going to be less than, remember I always put this to mean I'm leaving out some constants. This is going to be like something like n to the VC dimension times n to the t squared over 8. So this is when this is most useful. Okay? All right, so I know that that's kind of tedious to go through proofs like that, so I'm not going to go through all of them, but I do want to mention a few other theorems. But you should look through some of these proofs yourself because they all make use of the same trick, some sort of symmetrization. The next, I'm going to tell you a couple more theorems. I'm not going to do the proofs, but they often use the following fact. And this gets back to the question about the ghost sample, which is that we often end up in these proofs, you'll see, with quantities like this, which has the same distribution, first of all, whichever direction you do it, but in fact, each term has the same distribution because it's from the ghost samples from the same distribution. Let me state the theorem, and then we'll see if we want to do the next proof or not. This is another important theorem. This is just kind of another proof technique which relates a soup to the Rademacher complexity. And it's a little bit more general because, if I remember correctly, we are not going to require it to be binary functions. And here's the theorem. Let me state the theorem, and then we'll see if we have time for the proof or not. With high probability, so with probability at least, say 1 minus delta, Pn of f minus P of f, that's the thing we're interested in, the soup of that over some function class is less than or equal to 2 times the Rademacher complexity plus 1 over 2n log 2 over delta. That's theorem 23 on page 16. So I'm just trying to think whether we have time to do the proof and whether you have the patience to go through another proof. Let me just tell you how it works. And this is one you should read through. Okay? It's very similar, but it's not quite the same. Because the proof does 2 steps. Okay? So the first thing you do is the idea of the proof is you define, let's call it G's, yeah, I called it G, which is again this quantity we're interested in, the soup. That's some function, some complicated function. So let's look at this quantity. This is what we're trying to make a probability statement about. It's some complicated quantity. I think I didn't say it in the proof, but we're assuming that these functions are bounded. This is important for this proof. So add bounded to this. Because the first thing to notice is think of this as a complicated random variable. If everything's bounded here, and what happens if I change one observation here? You can see this changes by, this is an average. The only thing that changes if I change one observation is it can change by at most 1 over n times some constant because it's bounded. If I change one observation in an average, that average can change by at most 1 over n times some constant. And so we had McDermott's inequality. Remember the generalization of Hoeffding's inequality said that if something only changes a small amount when you change one observation, the probability that this is far from its mean is very small. This is an example where we use McDermott's inequality. So the probability that this soup is far from its mean is small. That's where this second term comes from. And again, you can read through this and see the details. I just want to give you the proof outline. The other thing to notice, though, is saying that this is close to its mean isn't enough because I have to say how big can the mean be. And that's where we use something like symmetrization again. So the core of the proof is just these 4 lines at the top of page 7. And I'll just do the first couple of lines so you see. Because we're saying that it's close to its mean, but we have to bound the mean. And the mean of something like this is kind of complicated. Because it involves a supremum. I'll do a few lines of this just so you see where we're using these tools. So if I say compute the expected value of the soup, that's not obvious how to compute that. But the key is to notice, again, I can introduce a ghost sample and say that if I have a ghost sample and I compute, I called it, Pn prime again, and take the expected value, because it's from the same distribution, that's P of f. So you notice in the first thing I do is I replace this with the expected value of Pn prime of f minus Pn of f. Okay, and then if you think about it, if you bring the expected value out to break the soup in, it can make it bigger. This is less than or equal to the expected value of the soup. I said I wasn't going to prove this, but I'm doing most of the proof. But I want to get to the key insight here.
Why is bigger?
Well, you can check that. Think about it. It's a general thing, right? What happens when you, how do soups and expected values behave with respect to each other? You can always check that it's always in one direction and the opposite direction for an inf.
It's because of average and max. Average versus.
Yeah, it's like the average versus the max, basically. But now, the cool thing is this. This is really, let's write out what this is. This is just I guess it's this one. I'm just writing out the definition of this. This is just this. But by introducing a ghost sample, see this has the same distribution as this. If you think about it, because they're drawn from the same distribution, I have two averages drawn from the same distribution. I compare them term by term. This is equal. Nothing changes if I throw in a Rademacher random variable. Let me say that a different way, that think I said this explicitly at the beginning of the proof. Let's say it here. Because the ghost sample is drawn from the same distribution, I claim this is equal in distribution. If you don't see this, you might want to prove this. Good homework exercise. In other words, I'm just saying, what does a Rademacher random variable do? It just flips this with probability half, or it leaves it alone. But they're drawn from the same distribution. So that doesn't change the distribution. The value can change, but the distribution, it has exactly the same distribution. So when I go to take the expected value of something, if I substitute a quantity with the same distribution, it doesn't change anything. It's got exactly the same distribution. That's the key step. So, and then after that, all I do is I take the triangle inequality. The sup of this difference is less than the sup of the first thing plus the sup of the second thing. And what is this? What is the expected value of the sup of this? That's the definition of the Rademacher complexity. This proof shows you where the Rademacher complexity naturally arises. So I went through that kind of quickly. You should go through the steps yourself. It's only 8 lines long. But it illustrates, again, the value of introducing a ghost sample, introducing Rademacher random variables, and that's where this first term came from. And the 2 comes because it's this one plus this one. I consider those 2 theorems sort of the main theorems that you need to know, that are good to be familiar with. There's a million of these theorems, okay? So there's lots and lots of theorems like this. But the basic VC theorem and this sort of Rademacher, direct bound based on Rademacher random variables, really give you a sense for how you reduce making a probability statement about the sup of some random quantities into something that you can control, something that you can bound. Now again, the Rademacher one, in some senses, always feels more fundamental, but really, it's pretty rare that you can compute the Rademacher complexity. So you often do see people bounding it above by something like the VC dimension and so on. But I still think it's good to know about the Rademacher complexity because there's a sense in which it's more fundamental. And in fact, what I really want to get to now are some applications of this. And I want to do, depending on the time, I want to do k-means clustering. Because that's one that is often not covered, and maybe density estimation. And the nice thing about the k-means one is, and I know we haven't covered k-means yet, by the way, but I'll remind you what it is. I probably, 9 out of 10 of you have seen it before. If not, I'm going to quickly remind you what it is before I tell you what it is we're trying to prove. But here's the interesting thing about the k-means case. The theorems you get, whether you use a VC approach or a Rademacher approach, you get different bounds. In fact, let me tell you what the problem is. And then tell you the 2 different bounds, and then we want to compare them. When is one bound smaller than the other bound? And the question of whether these bounds are tight is something that's only been actually settled within the last few years. So first of all, how many of you know what k-means clustering is? I would say that's pretty close, 9 out of 10 at least. All right, let's just remind ourselves, though, what we're trying to do. What is it we're trying to do with k-means clustering? So k-means clustering, so first of all, there is a population version of k-means clustering, and there's a sample version of k-means clustering. So just to remind you, I'm going to draw it in 1 dimension, although of course it doesn't have to be in 1 dimension. And you're picking centers. Suppose k was 4. You pick a k. K is 4. And these are going to be your cluster centers. And for you got some data points here. basically, remember what we're doing is for each data point, we ask how close is it to its nearest center, take the squared distance, and we want to minimize that, the sum of those things. That's the sample version of k-means. So the sample version of k-means is to find, let's call it C1 hat to CK hat, to minimize xi minus the distance to one of the centers, and then there's a minimum that says it's the closest center. And now we can think of that as a risk. Let's call that C hat. This is R of C. Right? That's what you're doing when you're doing k-means. You want to choose the center so that when I take the distance from each point to its nearest center, average that, I want to make that as small as possible. That's what k-means is trying to do. As you know, it's an NP-hard problem, so we don't ever do it. Although, do you all know about k-means plus plus? Who's heard of k-means plus plus, just out of curiosity? Okay, for those of you who don't know, if you ever do k-means clustering, you should always do k-means plus plus. Actually, not always. It's got some problems too, but it does get arbitrarily close with high probability to the minimizer. The minimizer is not possible to find in general, but there is something called k-means plus plus, which high probability gets close to the minimizer. It's a good thing to know about. But what are we doing when we're doing k-means clustering? What population problem are we solving? This is actually a general principle we should get into. There's algorithms. The usual algorithm for doing this is Lloyd's algorithm, right? Where you pick some initial centers, you assign each x to its closest center, then you take the average of those x's, that gives you new centers, and you repeat. That's the most common version of k-means clustering, right? That doesn't necessarily get you a global minimum, so people often repeat it, or you use this k-means plus plus thing. But what problem are we solving? What's the actual population problem we're solving? The population problem we're solving is, so this I should call this R hat, because this is like the training error. And remember, this is a vector of centers. Actually, it's a vector of vectors. Each one of these is a center, which is itself a vector. So it's a set of vectors. The population version is this. In some sense, this is just trying to estimate this. If you knew the true distribution, you'd say, well, where can I place the centers so that basically I get a center wherever there's a lot of mass, because that would mean with high probability that every x is close to some center. In fact, in the coding literature, this is called the quantization problem. This is called vector quantization. But in statistics and machine learning, we just call it k-means clustering. And so we're trying to choose the k vectors that minimize this quantity. But we're using this instead of this. It's just like when we're doing classification. We'd like to minimize the classification error, but we use the training error or something like that instead of the true classification error. Here we're using this training error instead of this, which raises the question, how close is this to this? Okay, so let me state the two results, and then we'll decide about which proofs we want to go through. So there's two different results. These are not the only results out there, but there's been some sharpenings of these results under certain conditions. But without making a lot of conditions, these are the sharpest results I know about. So theorem 25 says, suppose I minimize this. In other words, suppose you ran k-means clustering. And in fact, suppose you could forget about NP-hard. Suppose you had infinite computing, you get the true minimum. Let's imagine the best possible world. You're going to get some C hat, which again is some k centers, right? And if I look at the true distortion you're creating, I could ask, how close is that to the best possible choice? This is just like asking, what is the classification error of my classifier compared to the best classifier?
What is the best?
The best is the one that minimizes this. So C star is the set of k centers which minimizes if you knew the true risk. That's by definition,
The C hat is minimizer
of the training error, the one you actually get when you run the algorithm. Then this theorem, I think, I'm trying to remember who first proved this. It might have been Linder, but I'm not sure. Has the following form, which is so let's look at this bound. First of all, not surprisingly, the more clusters you're trying to find, the bigger is k, the worse is the bound. More disturbing is the dimension. If the dimension is big, that's not a very good bound. I should warn you, though, that even if these are close, does that mean that the clusterings are close? No. We're only saying that this risk, as we're defining it, or this cost, is close. You can have two clusterings whose risks are very similar, but the C's could be in very different places. The centers could be in very different centers. That's a much harder thing to control, and you need extra conditions actually to put a bound on the actual positions of the cluster centers.
What are the assumptions on the distribution of the X?
So for this theorem, it's assumed that it's on a compact domain, and I think that's the only assumption. And you don't even need to assume compactness, but then you have to have tail conditions. But let me state another theorem. Second bound, this is theorem 26. Sorry, it's not theorem, it's theorem 27. Here's another bound. It's k over root n. Why do we have two bounds? This was proved in 2008 by Biao, DeVroy, and Lugacy. And let's compare these two bounds. Which one's better? It depends, right? So in terms of the number of clusters, k, this is a better bound, right? Because this is square root of k, this is k. But let's look at the dimension, the effect of dimension. The dimension is d over n. Where's the dimension here? It's dimension independent. In fact, it's even true in infinite dimensional Hilbert spaces, the proof. Which is not just a mathematical curiosity, because look, if we're doing things like clustering functions and things like that, you're effectively in an infinite dimensional space. So which one of these is better depends on the scenario. Are you talking about large dimension? Then you want this, this is a better bound, and so on. So what's the difference in the proof? And now we have to decide. I'm going to tell you the idea, and then we'll decide whether to go through it. So this is proved using VC arguments, and this is proved directly using a kind of Rademacher kind of argument. So that the point being that it matters which style of argument you use. In this case, it matters a lot. So my plan, actually I did I include this proof? Yeah. I was planning, so I'm back to theorem 25. I was planning on going through it. It's just a basic VC thing. I'm not sure, we only have 10 minutes left. I'm not sure if it's interesting enough to spend a lot of time on it, but just to give you an idea, we can decide whether we want to go through the details or not. But let me just give you a feeling for what's going to go on in the proof, which is, if you think about the quantity, which is the distance of squared distance of a point to its nearest center. What does that function look like? Well, it's like a quadratic, right? It's 0 here, then it goes up, then when it's halfway in between, it starts to come down again. I didn't draw it very well, but I think you get the idea, right? That's for any point. I'm just computing what's the squared distance to the nearest center. And when you compute the expected value of a function like that, we're trying to minimize something over all possible c's. So what you get is a class of functions. But you can convert statements about the expected value of a function to statements about probabilities of being in sets, level sets of that function. Imagine cutting across this function. What do you get? You get things like this. Every level set of this function is like a union of spheres. And making a statement about the expected value of this thing we'll see, can be converted into a probability statement about what's the probability that the number of points in these sets is much different than their true expected value. This is exactly the kind of statement. In other words, we can reduce this to the proportion of points in a certain set minus the true probability in a set, the sup over A, where the sets A have the form unions of spheres. Well, we know that the spheres have a finite VC dimension. The union of k-spheres also has a finite VC dimension. And then the proof just uses the VC theorem. That if the probability of A, where A is a union of spheres, is close to the proportion, and if that's true over all of them, it's not hard to show that this expected value over any one of these functions is close. That's the broad outline of the theorem. I think in the interest of time, I don't think I don't think we're going to go through it unless there's a huge demand to go through it. But I include it for you. So it's the bottom of page 18 and the top of page 19, and it's just a nice example of how VC theory gives us a bound on something that people use all the time, and I think a lot of people aren't even aware that there's bounds like this. And oh yeah, I also included the Rademacher style proof on page 20. All right, so I don't really want to spend a lot of class time going through too many proofs. I hope you'll look through them, but you'll decide that. And maybe we'll see how it goes. Yeah, I think we have time. Let me just mention, we still have 10 minutes. So I'm trying to just get through what I consider to be the highlights of all of this material. You could have a whole course. In fact, we have had entire courses on concentration of measure, right? So you could spend an entire term on this. My goal really was to get through the VC theorem, and everything else is kind of icing on the cake. I just wanted to make sure I got through that. So those other things, like those proofs for k-means clustering and so on, I would encourage you to take a look at it. But I do want to mention that there's something else. Sometimes people get the feeling that all there is VC dimension, but there's other really important stuff, and that's covering numbers and bracketing numbers. So for example, and there's lots of different, we're going to use covering numbers in many places in the course. We're going to have some class of functions, like regression functions or classifiers, to deal with the fact that these are infinite a different way, a completely different way than the whole VC approach, especially when we're talking about real valued functions, so things aren't binary anymore or anything like that, is to just pick a finite set of the functions that approximates the whole set. So in general, when we have some metric, n of epsilon is called the covering number. It's the number of balls of size epsilon required to cover the space. This is a very, very, very fundamental quantity. It depends, though, on the choice of metric. For example, we might use the L2 distance, but maybe not. We might be using some other metric. And in fact, here's a bound similar to the VC bound, which uses covering numbers. So now I'm allowing this class of functions to be very general. It's not binary functions anymore. And the probability that this is bigger than epsilon is less than or equal to, let me write down the bound and then I'll tell you precisely what we're talking about. So what is everything here? I'm considering some arbitrary class of functions, but I am requiring them to be bounded, say less than b. And what is this? This is the covering number in the L infinity metric. What's the L infinity metric? Remember, that's just now there's actually better bounds. The L infinity metric is a pretty harsh metric. This can be a big number. There are better bounds involving better metrics, but I'm just mentioning this one because it's an easy one to do proofs with. Let's look at the bound. This looks a lot like the Vapnik-Chervonenkis theorem, except now it's very general. We don't have any binary functions. In fact, the VC dimension could be infinite, and yet we still have this nice bound. This is the number of balls it takes to cover this function space in the L infinity metric. These are things we can often compute. Just like VC dimension, the covering numbers have been worked out for many different spaces. This is actually not one of the best bounds, again, because the L infinity metric is, that covering number can be large. There's other metrics you could use here, like L2 metrics and so on, that have more complicated proofs but give tighter bounds. So I wanted you to be aware that there's lots more to concentration than VC dimension. In fact, most of the statistical stuff, like for regression and so on, they have infinite VC dimension, the sets of functions we're dealing with. Instead, we use bounds like this. And these will be coming up throughout the course. We'll deal with them as we go through the course. This proof is surprisingly simple. It basically amounts to, the proof is right there, and it basically amounts to the following. You choose some set of functions such that when I put balls around them, it covers the space. How many does it take? Precisely this many, n of epsilon, right? Except we use n of epsilon over 3. Then all you do is, for each function in here, you add and subtract the nearest one in here. When you add and subtract that, you create an error of size epsilon over 3, because it's an epsilon over 3 covering. And now you've reduced it to a finite set, and you apply Hoeffding's inequality. That's it. So in some sense, it's actually much simpler. Okay, and so what we'll see when we do minimax theory, for example, is these covering numbers come up all the time. And in regression and various places, we're going to mention these covering numbers. There's even something on the bottom of page 24 called a bracketing number. I don't want to overwhelm you. It's a little bit different than a covering number, but it's similar. But for our purposes, I think that's probably, we've covered enough of this stuff. Let me just tell you, so I want to tell you what's left in this set of notes, because that's pretty much all we're going to cover. There is some supplementary material. It's only there for your interest. There's something in particular called Talleyrand's inequality, which some of you may have heard of. It's basically, let me explain why it's there. Do you remember we did Hoeffding's inequality, but we also did Bernstein's inequality? And we saw in some, do you remember Bernstein's inequality from 705? We did it only on an assignment. If you've forgotten what it is, don't worry about it. If we need it, I'll tell it to you again. But it's all you have to know is it's an inequality that in some cases is tighter than Hoeffding's inequality. If we need it, I'll remind you what it is. But then we took Hoeffding's inequality and we got the VC theorem, which expanded it from a single average to a soup. Can you do the same thing for Bernstein's inequality? Yes, that's what Talleyrand's inequality is. So it's in the appendix for those of you who are interested. If we need it, we'll use it. But it does matter So for example, if you want to say that a density estimator is concentrated with high probability around the true density, Hoofding won't cut it. You need something like Talleyrand's inequality, it turns out. So there are places where it comes up. If it comes up for us, I'm not sure if it will or not. I'll certainly remind you what it is and we'll talk about it. Until then, I don't think there's any need to read that unless you want to. By all means, feel free to look at that material. So the takeaway message from all of this, I know I went quickly. If you're going to remember two things, Hoofding's inequality, the VC theorem. Those are the two big things. Any questions?
Is the covering number always going to be higher?
The covering number does not always have to be finite.
So then sometimes there is
Sometimes it's also infinite, and then you have other problems to deal with, yeah.
So then what's the point compared to
Because sometimes it's finite and the VC dimension isn't. Last thing, we're going to start now we want to go back closer to planet Earth. We're going to start linear regression. So what I really mean is high dimensional regression. So the regression notes are posted. Please take a quick look through them, and we'll start talking about them on Tuesday.